All right, next up. Our next speaker is a technical evangelist at Microsoft, a member of the Node.js Technical Steering Committee, and a chairperson of the Node.js Community Committee. And they are here to tell us all about the Node event loop. Everybody please welcome Bryan Hughes.
Hey everyone, thanks for joining in. We're going to talk about the event loop today, and specifically like how performance in the event loop works, specifically as it relates to like threading and processes, because there's actually some like really complicated stuff going on there. Before we dive into the event loop itself, let's talk about like multitasking itself, because this is a term that I think most people have probably heard, but there's actually a lot of kind of confusion around it, because there's like a lot of subtle details going into what this really means. Looking back in time, at least from like the personal computing perspective, I'm not going to talk about old school servers here in this, but from a personal computing perspective, the early computers could only run a single task at a time. So if we think about like MS-DOS and the various operating systems based on that, so like Windows 3.1, 95, 98, and ME, and then also on the Mac side as well, like the original Apple OS and then the early versions of Mac OS as well, basically you can only run one thing at a time. You can think of it as only running one program. There was no ability to run two programs simultaneously. There's also no concept of like a background process or background program or anything like that. You had one task and that was it. Of course, that's really, really limited, so not long after we created a thing called cooperative multitasking. And this definitely helped us out quite a bit. And the idea with cooperative multitasking is you can have two processes, you can think of two applications running side by side. And then inside of the code, if you're the developer writing the code for one of those processes, you will explicitly add in code that says, okay, I can go ahead and stop and pause now. Usually this is in the form of a function called yield. So what the operating system would do is it would get your program executing, and your program would just keep on executing and going along until it hit one of these statements. And at that point, it would kind of stop and allow something else to run. That other thing would run until it hit a yield as well. And you'd sort of switch off back and forth that way. And you kind of got the appearance of multitasking. And this is pretty common for a while, and it's still common in certain situations too. But there are definitely some limitations to that. The key limitation to this is, well, what if that application just never calls yield? You have a bug or something, and you just skip that branch. Well, then that one application will run forever and prevent anything else from ever running. So it's kind of a problem, Apps have bugs. And so if you can centralize that logic, it's a lot better. So the next step was to create this thing called preemptive multitasking. And once again, this is a thing that the operating system does, just like cooperative multitasking, except in this case, the applications themselves don't have to do anything at all in order to switch between different applications. What the operating system itself does is it will run a task for a little bit. It will pause that task. It will actually take like the contents of the CPU registers and like the things that are actually executing, and it'll like save those somewhere else. And then it will switch over to another task and like run that one for a bit, pause it, save its state, switch back to the first one. And it'll like flip back and forth pretty rapidly. And that way it gives the impression that these two processes are running at the exact same time, even though you only have a single processor. And so like this really helped a lot. And once we started getting operating systems that supported this, we really started to see a lot of growth in applications. So once again, on the Windows side, we first got preemptive multitasking in the NT kernel a little ways along. So like NT 4.0, that was one of the big bonuses to that. That's why it was big in businesses back in the day. Then Windows 2000, and then finally Windows XP. So when Windows XP was released, it was actually a major shift. It got rid of the old lineage from the 9X days. And then same thing in the Apple world. So Apple added some sort of variants of this to Mac OS 9. It didn't really work, so we'll ignore that. But so like finally kind of got it properly in Mac OS 10.0. And we have proper preemptive multitasking. And that's because preemptive multitasking has been in Linux and Unix land for a really, really, really long time. They were the first ones to really do that. So like things are getting pretty good. But it turns out we could actually do a lot better. And this is where like a lot of researchers were looking at ways of getting hardware support for the operating system to do a better job of multitasking. And the researchers ended up coming with a thing called Symmetric Multi Threading. Intel branded this, by the way, as hyperthreading. So if you ever saw like a branded thing that said hyperthreading, that's just the brand name for symmetric multithreading. And so what this technology does is you can give some hints to a CPU that says, I have these two things that are running in parallel, and the CPU will take that into a single core. So this is a single process, or a single processor, basically, is still able to, in some cases, parallelize these things inside of the processor itself. So you have a single core that's running, but there's certain parts that are like parallelized, actually. If you ever look at an actual diagram, there's usually duplicates of a lot of things. There's duplicate floating point units, arithmetic units, and things like that. So like the processor is able to sort of kind of parallelize this somewhat without having to have two separate processors. Now in practice, in modern days, we have multi-core devices, so we have multiple processors, and then each one of those processor cores also has this like a virtual processor, as we call it. And by kind of getting the OS, the various operating systems to support S&T really well, we were able to get some speed up on top of even preemptive multitasking. And that's basically where we are today. So now this very last thing I said, symmetric multi-threading as opposed to multitasking, and I also mentioned processes. So it's a lot of words I'm throwing out here. You can more or less assume that multitasking and processes are, or a task and a process are basically the same thing. The task is like a general word, and a process is a very specific word that has a specific definition in the operating system. But they're basically the same thing for the purpose of this talk. Threads are really different, though. So I want to talk about the difference between those two. So a process is basically like an application. We can think of it as a container that is running a set of code. And that piece of code is completely independent. The big thing is that inside of a process, it has its own memory space. So whenever you have multiple applications running, the operating system is going to take each of those applications and fit them into different parts of memory. The idea is that we don't want them to overlap, otherwise it means programs can start messing with each other. In fact, that's how a lot of like viruses and stuff work. So processes always have separate memory, and if you want to get two processes to talk to each other, you have to actually create a communication channel between them. This is usually referred to as inter-process communication, or IPC. Now, IPC is not a specific technology. It's sort of the name for a class of technologies. Typically, IPC is done using a socket of some sort. This can be a TCP socket, but it usually is what's called a Unix domain socket. And it's similar to TCP, but just a different protocol. And it's meant for like local connections on a single system, as opposed to going out over a network. So less overhead, stuff like that. But this does mean, though, just like with TCP, if you want to send a message from one process to another, the first thing you have to do is serialize it and put it into a packet, meaning you have to have something that can be turned into a string somehow. So in the JavaScript world, this basically means it has to be something that we can pass to JSON.stringify. If you've ever tried to pass a function, or say like a function that's a property on an object into JSON.stringify, you get an exception. Because there are certain things that cannot be serialized. And so this is sort of a limitation with processes. Now, threads are a different thing. Threads are also a mechanism in which you can run two pieces of code in parallel, but they're inside of a process. So like all processes have threads. You can think of it as a process as being like a parent to a thread in a sense. And you have multiple threads inside of this one process. Now, because they're inside of a process, that means that all of the different threads have access to the exact same memory. So you can declare a variable in one thread and access it from another thread. And so this gives you a lot of optimizations that you can do on top of, instead of like what processes can do. Like especially if you have a really, really big data set, think about like encoding an image or rendering a scene, then you want to be able to access a single buffer, but you want multiple threads working on it. And there's a whole bunch of different ways in which you do communication around that. And they tend to vary from like language to language. Like there's a way you do it in the JVM, and there's a different way you do it in the CLR, and so on and so forth. So yeah, these are pretty awesome, but there is a downside to it. If you have two threads that can access the same variable, you can run into bugs really, really easily. So especially in a modern system where we have multiple cores, you can have two threads that are actually running at the exact same time. And if they both try to access the same variable at roughly the same time, especially if, say, one is going to write to that variable and the other is going to read from it, well, you run into this issue where you cannot guarantee what order that will happen in, at least just innately. It depends on how fast each of those threads run. It might be that thread A writes to this variable first, and then thread B reads it in one instance, but the second time you run it, it's reversed. And that actually gives you a different result, and that's a bug. So you have to like manually write in code in your threaded logic to make sure that you don't run into that bug. You usually have to tell one thread to like hold up and wait for a bit, and let the other thread catch up and make sure that you're sort of on the same page. And doing this code is actually really, really hard, as it turns out. Writing threaded code accurately is really tough, even for experienced engineers. And so a lot of modern like runtimes have been looking at ways of, how can we take advantage of, these multi-core hardware and virtual threads and like all this other kind of stuff, but do it in a way that is a lot easier to program. And so Node.js actually has a very specific answer to this question. And the big way that it accomplishes this is to just not mess with it. There are no threading primitives in Node.js that you can access. And so this is what we're kind of talking about when we say that Node.js is single-threaded. The thing is, Node.js is single-threaded, except when it's not, as the slide says. So we'll kind of talk about that a little bit more. So inside of Node.js, all of your JavaScript, in addition to V8 itself, as well as the event loop, all runs in one thread in one process. And there's nothing you can do about that. That is just the way that Node.js works. And so when people say Node.js is single-threaded, this is what they're talking about. Like, it's not possible in Node.js to have two separate pieces of JavaScript run in two different threads inside the same process. You can spin up multiple processes, but it's not really the same thing. And so by doing this, we just get rid of that entire class of problems that comes out from writing buggy threaded code. But we still have to take advantage of this hardware. So what do? Well, it turns out whenever we get to C++, there's a very different story. So a lot of Node.js, about half of the source code last time I looked, is written in C++, and the other half is written in JavaScript. And so on the C++ side, we do have access to threads there. But first, if you ever call a synchronous method that's backed by C++, so any API built into JavaScript is backed by C++, if it's synchronous, it will run on this main thread. However, if you call a C++-backed asynchronous method, it may run in the main thread and it may not. It actually depends on the circumstances. So to talk about what I'm talking here, we're actually going to take a look at some examples. The first one I'm going to do is from the crypto module. I'm using this specifically because the crypto module has some very processor-intensive methods on it. There's a whole bunch of math that it has to do, and it can tie up a processor for a while. So first, we'll take a look at just some straight-up synchronous code. This is calling PBDKF2, which is a hashing algorithm. It's a very modern one and intensive. So if you have passwords, things like that, if you want to hash them for security before you put them into a database, this is the method that you use. Now this is the synchronous one. In this case, I'm showing off two requests, and we're going to call it twice, and then we'll take a look at the execution graph. So it's synchronous, and we get an execution graph that looks like this. This is basically what we expect. We call this hashing method the first time, and it's going to go and run to completion. Because it's a synchronous method, it's actually going to block all JavaScript execution, and it's just going to wait at that point until we're done. And then once that's done, it can call the second one. And we see that in the graph where we see the first call and then the second one right after that. Now there's also an asynchronous version of the same method. This is crypto.pbdkdf2, without the sync part. And so this is a very common pattern you see in Node. In fact, there's a reason that all of these synchronous methods add sync to the end, but the async methods don't have the word async on them. The idea is that we want to say that synchronous methods are actually not the right choice in Node. You should try to use the asynchronous ones if at all possible. And the reason why we'll actually see here in just a second. Once again, the same code, except asynchronous. And that's because we get an execution graph that looks like this. So you can see, instead of running one and waiting for that to finish to start the second, they actually run at exactly the same time. So by using the asynchronous version instead of the synchronous, it took us exactly half the amount of time to complete that entire operation. And that's because these things are asynchronous. They're going to C++ and going up and doing interesting things. Like when you're using an asynchronous method, it allows whatever work that method is doing to be shipped off and done somewhere else, and you could do them in parallel. So that's really cool. Always use asynchronous methods. This is why. Now let's say we decide to, instead of do 2 requests, we do 4. So with 2 requests, we can see it took a little under 150 milliseconds to complete. With 4 of them, though, this actually increases to a little under 250 milliseconds. So we ran them in parallel again, but it took longer. So what's going on here? Well, it turns out these benchmarks were run on this laptop right here, which has a dual-core processor in it. So it has 2 physical cores, but also has symmetric hyperthreading, which you talked about earlier. So it means there are 4 virtual cores. So what's happening is because this crypto method is very CPU intensive, we still have to do that work, and we have a limited number of cores. So it's going to take 2 of those crypto calls and put them onto one core, and take the other 2 and put them onto the other core. Now it has symmetric hyperthreading, so we get some benefits to it, which is why it's not twice as long, it's a little less. But nonetheless, we're just seeing that those cores are taking time and it's having to sort of switch back and forth in a preemptive multitasking style. So, all right, so that's once again, just know that the limitations of your hardware can ultimately, fundamentally limit what you can do code-wise. Now, let's increase this up to 6 requests. With that, we get this graph, which is really weird looking, right? So let's go and superimpose all of those requests together. So what we see here is we go from 2 to 4. There's an increase because that's just the limitation of the hardware. If this were a quad-core machine, all 4 would have been the same as 2. But then there's that weird tail. So this is actually hitting a different limitation. This is not an operating system limitation. This is actually a Node.js limitation. So what is happening with crypto, whenever we make these calls, there's some C++ method, like a pbdkf2 C++ method, that Node is calling under the hood. And it's the same method whether it's synchronous or asynchronous. And so to make those asynchronous calls run in parallel, Node will automatically run those in separate threads. So Node.js has threading under the hood. But the thing is, it doesn't spin up a new thread for each request. Instead, Node has what's called the thread pool. Basically what it does is whenever Node starts up, it will create 4 background worker threads for you. By default, you can change that number, but it is 4 by default. And so those threads are always running. And whenever something needs to be run in a background thread, the event loop will ship that code off to one of these existing threads in a round-robin fashion. So it'll take that first request, put it into the first thread, the second into the second, third into the third, fourth into the fourth. When that 5th request comes through, though, Node's going to say, oh, hey, I'm actually out of threads. They're all busy doing other stuff right now. So it's going to queue those requests and wait until one of those threads in the thread pool becomes available. And so what we're seeing in that previous graph here is it's running those 4 in parallel, and then once that first one finishes, which they all finish at about the same time, it will then take that 5th request and pop that into the thread, and it'll take the 6th request and pop that into the thread. So it's really like running 4 and then 2 after it. And so this is where you want to be really careful with how many simultaneous requests you're doing at the same time, because you can run into this thread pool limitation. So the next example I want to show off is you making an HTTP request. So this is a much more common thing that we do in Node. Node, we're oftentimes doing some sort of networking. We're either making requests or accepting requests. So we'll take a look at some code here. We're doing http.request from the HTTPS module. This is downloading my profile photo from my website. I chose this one specifically because it's a large photo, about 800 kilobytes. It's hosted in Azure, which has really consistent throughput and latency throughout the system. And also, it is not behind a CDN. CDNs are great for performance, but they also make the performance a little less predictable. And I wanted predictability just for the test. So we're going to download that. We're going to listen for our data events to make sure that it's actually going to download all of the data. And then we're waiting for that end event. And so we're going to measure how long it takes us to get that end event. So we have 2 requests, and it takes about 700 milliseconds to download each one of these. And you can see they're actually pretty consistent. So cool. All right, we'll increase to 4, just like we did earlier. And so now this is different. This is actually kind of interesting. You see, for the 4 of them, it still took 700 milliseconds. It didn't take an increased amount of time. Now that's because this type of work is actually really different. Crypto code is all about doing a bunch of math. So it's sitting in the processor doing stuff. When you're making a network request, most of the time you're just waiting for more data to come in. Like your computer is actually not doing very much when you're downloading something. So there's no like CPU cores to saturate. You can end up seeing a limitation in network bandwidth. Like there's always some sort of bottleneck in every system. But we aren't hitting that here. So all right, makes sense. Let's go on to 6. Now this is really interesting though, because now we have 6 of them running at the same time, and we can see it did not increase the amount of time that it took the last 2. This behaves totally the opposite from what we saw with crypto. And there's actually a reason for this as well. And that's because under the hood, inside of Node.js, anytime we can use a C++ asynchronous method, we will. It turns out C++ actually does have mechanisms to do asynchronous calls. Now, the way that C++ does it, though, is it's very different from Node.js. For C++, it's actually the operating system kernel itself that manages those for us. In C++, you basically tell the kernel, do this operation, and then I'll check back over time, and you tell me if that operation is done. So you're basically like registering to listen for, they're basically like events, is what you could think of. Now, because this happens inside of the kernel of the operating system, that means that it's going to vary from operating system to operating system. So there is no uniform asynchronous method for C++. Node.js specifically uses what's called epoll on Linux, which is one mechanism. It uses KQ in macOS, which is similar to epoll, but a different API. And then on Windows, it uses getQueued completion status EX, which is, of course, its own API that's a little more different from the other two. And so whenever Node can take use of these kind of mechanisms, it will do it because this mechanism is not actually running separate threads, so we don't have that overhead. And so anytime you have HTTP, things like that, you're not limited by the effects of the thread pool. All right, so I've been talking, this whole talk is supposed to be about the event loop, and I haven't really mentioned it very much. So I'm just going to skim over it because I kind of want to focus on a very specific part of the event loop, and that's performance. But what we can think of the event loop as is it's sort of like a central dispatch. It's like a director inside of Node.js. It's a central piece of software that sits right behind V8. So you make a call in JavaScript to some Node API. It's going to go through some like JavaScript. There's some pre-processing in JavaScript. We do as much in JavaScript as we can. But at some point, it's going to jump from the JavaScript side of V8 over to the C++ side of V8. V8 does have a C++ API that we can use. And so once it jumps to that C++ side on V8, it gets sent off to the event loop. And like everything goes through the event loop. Every single request in Node gets sent over there. And then the event loop is going to take that and direct it off somewhere else. So for example, if this is a mechanism that needs to be run in a thread pool because there's no native things, the event loop is the one who is going to figure out which thread to send that to. And then also once the work is done in that background thread, it will signal back to the event loop to say, hey, I'm done, and here's the result. And then the event loop is going to ship it back off to anyone that's listening for that incoming information. Conversely, if it's based on epoll, it does something pretty similar. Now, if it's using a thread pool, it is being sent into a background thread. That's kind of the definition of what a thread pool is. However, if the call is using epoll, KQ, or something else like that, it's actually not sent to a background thread. That is actually code is actually all run in the main thread. The reason being is most of the actual work being done for that is being done inside of the kernel itself, so it's already not blocking our system. Now, this is an oversimplification. The Node event loop does a lot of other stuff as well. It manages like timers, it manages whenever it's time to shut Node itself down, and a bunch of other things like that. And there's some resources at the end where you can learn about what that's doing there. But for the purpose of this talk, think of it as this sort of scheduler. So the big question, of course, is which APIs use which asynchronous mechanism? This is the part that you really want to know. I'm also going to note, I kind of shamelessly borrowed this slide from Bert Belder, who created it for me. Bert actually does some work on the event loop, so he kind of knows the system a little better than I do. But anything that does kernel async, that means epoll, KQ, things like that. Anything that is TCP or UDP, so all of your networking requests, whether it is a server or a client request, is going to be done using kernel async. So you can just get as many of those requests going as you want, and the threading is not going to be the limit for you. Now, if you keep handling more and more requests, you can still run into issues with network latency, memory sizes, and things like that, but you're not going to be limited by this threading model. Same thing with pipes. So if you're reading a file, let's say you want to read from one file and you want to pipe it to another, that actual pipe part is going to be done inside of the kernel. And there's other things you can pipe, like you can pipe networking streams together. So if you have a client request, you can actually pipe that into a server response. And all of that is handled by C++ under the hood inside of the kernel. Also, all of the DNS.resolve calls, all of those are also handled by the kernel. And basically, sort of the theme here is that networking is handled by the kernel, as well as a few other things around that. Now, the thread pool, every single file system operation uses the thread pool under the hood, because there just isn't a C++ async method for that. So if you're doing lots of file I/O, well, you'll probably be disk-bound, but you might actually run into this issue as well, in that you can basically only have so many writes outstanding at a time. Now, in practice under the hood, the file system module does chunking, so it's going to write a little bit here and there. So it makes it look a little bit more like they're running in parallel, but you're still kind of running into this limit. DNS.lookup itself also doesn't have an async call. It seems like that was just sort of the omission from the DNS capabilities in C++. And then there's also some edge cases with pipes. Like in certain cases, pipes are actually not going to be done in the kernel. It's like the kernel can only do certain types of pipes, basically. Now, we do get into some differences in Unix systems versus Windows systems, and this is going back to the differences in the kernels. So on a Unix system, all of your Unix domain sockets, the thing I was talking about earlier that's often used for IPC, Unix domain sockets are handled by the kernel, and so they're not subject to this thread pool limitation. Same thing with TTY input. TTY input, by the way, that basically means you're reading from the console. You're doing standard in, standard out, console.log, stuff like that. Also, if you happen to be writing to a serial port, this would also qualify since that's a TTY device. Any sort of Unix signals, so this is like SIGINT, SIGTERM, things like that, if you happen to know what those are. And then finally, child process. So if you're going to call child process that spawn, exec, things like that, that is not being run in a background thread. That is being handled by the kernel. On Windows, it's a little bit different, though, because those three things I just talked about, so child process, TTY input, those two things are not handled by kernel async, and so those are run in the thread pool. There's also a couple of edge cases for TCP servers in Windows where we end up having to shell out to thread pools a little bit. And yeah, that's pretty much what Node does. There's a whole bunch of other little APIs here and there that we can look at and figure out. Most of them are synchronous, so they're not included here. But yeah, so that's the kind of thing to keep in mind, like when you're writing a lot of code. If you ever are writing code in Node and you start seeing some really weird timing, like things aren't happening at the time you thought they would, something is being delayed a bit, the thread pool, this is the kind of thing to look at, like, what is your thread pool like? How many threads are being used? And so you can look at it based on this table here to see what is your code doing and which parts use the thread pool. If you want to learn a lot more about the event loop, there are two classic talks. The first one is by Sam Roberts. The second is by Bert Belder. And that takes a very different approach, and they talk about internally how the event loop works. And I'll put these slides on Twitter as well so that you don't have to write it down right now. But both of these talks talk a lot more about the internals. And so you can learn more about how the event loop works, and it actually sheds a little more light on some of these performance characteristics as well. And there's also a really good blog post by Daniel Kahn that dives into this a little bit more in depth. And with that, I want to thank everyone for listening in. And if you have any more questions, I'll be hanging out the Microsoft booth for about the next hour. And if you want to chat about anything about Node.js, anything else Microsoft related, come talk to me then. And thanks, everyone.